So since we're doing D1, okay. Okay, so let me just get that up. I have that. Okay, let me just open up the thing, yeah? Where is my astrophysics? Ah, okay, I got it. Hold on, give me a couple more moments here. Here's it. Okay, so I have here something about the options. Okay. All right, equations. What exactly exact equations we have here? Um okay. Astronomical distances. Oh, okay. And then we have, okay, so the equations we have according to my notes here and the books I'm looking at. Okay, so astrophysics D1. Okay, equations. Okay, first of all, we kind of started it last time we met. Oh, speaking of the meeting, speaking of meetings, Sunday, right? Yeah, that was last Sunday. I just remembered. You got charged for it, right? CJ, you there? Hold on. Hello, CJ, can you hear me? All right, there. Okay. All right, so let's go back. I think just something went off with my connection there. All right, so anyway, since we're dealing with the equations for astrophysics, um, okay, according to the data booklet that we have here, IB Physics data book. Let's see. Physics data booklet. All right. Just take a look at the three equations we have in the data booklet for D1. Okay. These are actually pretty easy to understand. Okay. but we really have to take a look at why that's the case, right? Okay. Okay, there we go. I think you can see that. And I'll just share my screen either way. Okay, so these are the equations in the data booklet for D1, right? This is a pretty, the first one is pretty straightforward equation. We kind of discussed how this goes. Yeah? Right. So you have to convert your angle into arc seconds first, and then from your angle, this P stands for angle, okay? Okay. I'll explain later how this works. Yes. Are you aware of that small angle approximation we can use? No. All right, that's fine. I'll explain. Yeah. Yes. But yeah, that's correct. Large. Okay. All right. Okay. The second equation here, all right? This is just you haven't if you haven't done a what's this? Topic 8 yet, you wouldn't understand what this equation means. Okay? I'm just going to label these first, what the symbols mean. No. Okay, I'm gonna have to label all of these, right? So the first one, L, I'll just okay. L is luminosity, correct? Okay. Yes. Basically, you can just think of this as light intensity. Okay. The reason why I prefer calling it as light intensity is simply because in topic 8, it's the exact thing that it's defined as. Okay. All right. Because why is it like this? Because I'm gonna show you the equation. You don't have to know the actual equation just yet, but the exact equation in topic 8. Let me get to that. I'll show you that exact equation. Where is it? Okay. This is the equation from topic 8. Hopefully that includes. Okay. You see, there's really similar, right? Yeah. Okay. There's an. Okay. In this case, P stands for power. All right. Okay. Here, this E. I'm just gonna tell you what this E means here. How this E is. This E is actually also here, but in this case, E equals 1. Okay. Now, in topic 8, this E stands for the emissivity, but we'll not define it yet. I'll just let you know what it stands for. Emissivity. Okay. So E is emissivity. Sigma is a part. In a manner of speaking, yes. All right. Okay. The A here stands for area. Okay, I think I'll just put it here like this. So A is area. Now, specifically, this is area of the sphere that the star is at the center of. Okay, so again, A is the area of the sphere that the star is at the center of, and then T is the temperature in kelvins. Okay, and finally, that sigma thing. I'm just gonna write it down like this. Sigma. Okay. This is the Greek letter, by the way. This is what's called the Stefan Boltzmann constant. Stefan Boltzmann constant. Okay. In the data booklet, this has a value. So I'll just copy that value straight from the data booklet here. Where is it? Sigma. Okay. This is the value in the data booklet for the Stefan Boltzmann constant. Okay. All right. That's all it means. Now, what does luminosity here basically? This is the amount of radiant power that a star, that the star basically emits, and that kind of depends on how far the star is from us, and how bright the star actually is. And how bright the star is depends on its temperature. Okay, so again, so let's write that down. So the L equation basically means that stars brightness depends on the temperature, its temperature, and its distance from us. Okay. Okay, so the second equation is this. Okay. All right. Now the third equation, what does this mean? This B here, this B is called the brightness, apparent brightness, correct? Okay. 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 Kind of, right? Because the third equation now tells us, the third equation exactly tells us how exactly we perceive its brightness. Okay. Now tells us how we perceive the star's brightness. Okay, that's it. Okay, so these are the three equations for this particular unit. Okay. All right, so I'll give you an example first. Let's try to explain the first one, the parsec equation. Yeah, so the parsec equation, the d in parsec equals this. This I'm gonna ask you to do something in a calculator. So d, okay, okay, equals 1 over p in arc seconds, right? Okay. Okay, so this, let's kind of take a look at that again. We kind of established the fact before that for parsecs to be useful, this has to be a small angle theta, right? Or in other words, that's your p, right? Okay, now let's say this is 1 AU, right? And where's the 1 parsec? This is the 1 parsec, right? 1 PC, right? So if you look at this in trigonometry, what is tangent of P? Opposite over adjacent, which is 1 astronomical unit over 1 parsec, right? Now here's, okay, now the thing here is, since this angle is small, right? Very small. What I want you to do is in radians, set your calculator in radians. Especially in radians. Okay, now I'm gonna ask you really quick. Can you find tangent of 0.001? Or let's turn it into an actual parsec. Can you calculate this? What is 1 over 3,600? 1 over 3,600 would be how many? It would be 2.7. Okay. 2.7. Let's put it to 2.8, right? Times 10 to the minus 4, right? Okay. Now, can you find the tangent of that? Yeah. Yep. No, no, just tangent. It's basically the same thing, right? Do you get the almost the exact same number? Almost. So slightly smaller, but rounding it off, it's still gonna give us 2.8, right? Okay. Now this works because of a mathematical trick. Okay. This works. I won't tell you how the trick actually works itself. Okay. The mathematical trick that this relies on is that tangent theta is that sine theta, sine x, I'll use x, yeah, is equal to x plus, no, minus first, x squared over 2 factorial plus x to the 4 over 4 factorial. And you see the pattern here, right? Over 6 factorial plus so on. Okay. All right. So you will see here, because of this trick, from this trick, we can basically get that for small x, right? Small, also cosine x. I'm going to do cosine x as well. Cosine x is equal to 1 minus x over 1 factorial plus x cubed over 3 factorial. You get the pattern, right? Right? Okay. Okay. Hold on. Did I do that right? Okay. Okay, I think I made a small mistake with this. Yeah, I made a small mistake. But the idea still stands. There's still a pattern. Yeah? Alright. This is gonna be 3, then this is gonna be 5, this is gonna be 7. In other words, sine has the odd powers. So this is gonna be 3 factorial, 5 factorial, 7 factorial. Then cosine will have the even powers. So this is gonna be squared here, 2. It's gonna be 4 factorial, and so on, right? Okay, but the trick here is, if you look here, the trick is, once you get to very small values of x, right? I'm not gonna write it here, but once you get to very small values of x, sine x is basically x. All of these disappear for small values of x, right? Then cosine x, for small values of x, also these disappear, right? For very small. You didn't know this because you're not taught this. I also don't normally see this taught to like the math students in my class, so I usually just say it like this. Okay, but this math trick basically tells us that even if you have a very tiny angle, this also disappears, the x squared over 2 factorial thing, right? So what is tangent theta now? Tangent x for small angles, we get x over 1, which is, well, approximately x over 1, right? Which is approximately x. So that's why this trick works. That's why this particular equation works, because of the fact that this math trick works. Okay. Okay. So so from here we can rearrange anyway. So now that we're clear with the math, even though you're not expected to know it, but it makes more sense now, right? Everything kind of makes more sense now, right? So I'm gonna write this now as P is equal to 1 AU over 1 parsec, right? So I'm gonna rearrange. I'm gonna put 1 parsec onto the we're gonna exchange P and that. Hence we have this formula. Helps you remember it even though the data booklet's in there, right? Okay.
So is it? I thought I was looking for distance, so now I'm looking for the angle.
So you can use, yes. So either you're given the distance in parsecs and you can determine the angle, or you're given the angle, you can determine the distance in parsecs, all by doing this trick. Just swap it around.
Oh, this is called the parallax.
Yes. That's why P. That's why it's called P for the parallax angle. Yeah. Ah, let me note that here. P is parallax angle. Okay. All right. So okay. Now, of course, this doesn't quite answer the fact that this should be in arc seconds, right? Because so far we've done it in radians, right? Now, the parallax angle is now defined. If we now measure the parallax angle in arc seconds, the AU just disappears because of the definition of the parsec. Okay. So, okay.
Okay, because it's always expected that it's going to be 1.
Yeah, it's always 1 AU anyway. So this 1 stands for 1 AU. Okay. All right. So anyway, so that's how we got this formula. The second formula here, again, it's based on this equation. Basically, to further understand this simply means that any body that has a temperature will emit radiation with this much power. Okay. And then the third one is basically, okay, it's gonna be something like this. The second and third equations, I'll explain briefly why that's the case. Yeah. Then afterwards, we're just gonna go straight to problems here. Okay. Why do these two equations work? Basically, okay, hold on. Let me get an image off the internet. Just make it easier. Let's see a good image. That's not such a good image. Okay, I think I better just draw one. It's gonna be easier. All right. So anyway, so let's say that this is our star, right? Star. Okay. Now around that star is gonna be a sphere, right? Okay. Now let's just say that on somewhere on this sphere is Earth. Okay. So let me just note that there that this is a sphere. Okay.
Doesn't the atomic unit itself have a lot of uncertainty?
It does, but by definition, the astronomical unit is actually defined as the average distance between the sun and the earth, and that has a precise value. If we remove the word average, yes, that problem becomes problematic. Yeah. All right. So going back here. So this, I'm gonna to make two distance measurements. This distance r, which is the radius of the star. Okay. Okay. And then this distance d, which is the distance between the star and the earth. Okay. Star and earth. Okay. All right. Now you will notice we don't really use the word sun here. We don't use the sun as our measurement. We always use the earth. It's the simple reason is we're on earth. We're not on the sun. Okay. All right. So let's go back to how to derive these. Okay. This brightness here. Okay. This is where you apply brightness. Okay. All right. Now, where do you apply luminosity to? You will apply this equation, the luminosity here. Why? Because that radius of the star is going to give you a surface area of the star, right? Because the surface area of the star will be equal to pi 4 pi r squared. Okay. So, okay. Basically, that's it. Okay. And then you go back here. Okay. Is this clear on how to find the luminosity?
You said do it at the where the star is, or the radius of the star.
Mm-hmm.
So we find 4 pi r squared and then plug that in.
Yes. Yes. Now,
So we're
not actually done yet, but that's the idea there. All right. Now, okay. Here's another thing though. That luminosity now here's the thing. Look at this. Isn't this like an area? Right? Right? So what you can do here is actually, if you think about this luminosity and the apparent brightness, they are related not just because of the fact that they're made by the same star. They're related by the same basic equations. Because if we rewrite this third equation, it becomes L equals B pi times 4 pi d squared, which kind of becomes L equals B times the area, right? But if we compare that to the other equation, A here, and then we have sigma t to the 4, you can kind of look at this, that the apparent brightness,
wondering if capital B was like absolute.
yeah, all right. Actually, it is, but we're not interested in that. Uh,
Oh,
okay. Let me go back to that statement just in case I'm wrong with it. Yeah, but anyway, either way, this is small b. So if you kind of look about this luminosity, the apparent brightness, look, the apparent brightness is just basically dependent on the temperature of the star. Okay. So what does this tell us? If you look at a star, you can either calculate its luminosity or calculate its brightness, depending on what you want to look at. Right?
so B can equal Boltzmann constant times the quartic, no,
Mm-hmm.
quartic temperature.
Yes.
So like that equation can be
Uh,
like
yep. Okay. All right. Luminosity, apparent brightness. Okay. Or here's a better explanation of it. I think this is not quite so obvious, right? So this is the better explanation. I've looked at you can think of it like this. This is again the star, right? And again we have that sphere around the star, right? And then this is the earth, right?